of tungsten 18. So, what we have is from our calculations, we see that the HOMO-LUMO gap, theoretically, is quite different. We see that the actual LUMO energy certainly is very different, but the absorption is fairly similar. So what we looked at to test it, in general, first of all, was palm photoreduction. What happens if we just shine light on it in DMF? In this situation, we would take the fully oxidized polyoxometalate in DMF, we'd shine light, visible light, and the solution would go blue. Just like I showed you at the start of the talk. And it would see something like that. So that would be our singly reduced polyoxometalate. What we found when we irradiated over 390 nanometers was we got our compound 1 reduced fairly well. P2W17 didn't reduce at all. P2W18 a little bit. And actually it reduced to the 2 electron reduced species, which is a different story. At 420 nanometers, compound 1 reduces again by 1 electron relatively well. And P2W18 almost doesn't reduce at all. So it's a very good sign. The fact that our POM is photoreduced by 420 plus nanometer light is a very, very good sign, because what's happening is you are, we think, oxidizing the DMF. So we wanted to test it in a model system. We did indigo dye decomposition. It's been done by a few groups as a kind of simple test for going via this kind of oxide radical mechanism. Indigo is a very, very dark colored dye, and we put our POM and indigo into a cell. We irradiated it, and we watched it go colorless. So this is almost the opposite way around to the previous example. And what happens here, the indigo peak drops down to nothing. What we think happens is that the POM goes to the oxo radical. It's then probably solvent mediated, we think. We get to the reduced polyoxometalate. This most likely DMF-based radical attacks the indigo. And we reoxidize the POM by air. So, that's our model system. The results were, at 390 nanometers, our blank and our tungsten 17 are very, very similar. Tungsten 18 does a little bit. Our compound 1 is pretty good. These are pseudo-first order rate constants. At 420 nanometers, tungsten 18 is basically almost blank. Our compound 1 worked fairly well. So, this is, I guess, a start point in this photosensitization of the real POM photochemistry for us. And there's more stuff that I'll present tomorrow leading on from this. The final area I want to talk about, if we just go back to the scheme of where we're looking. In this situation, we're going to look at some more soft materials. Hybrid POMs for redox active supramolecular assemblies. This work started off with this molecule here, long chain thiols attached to a polyoxometalate. And we were basically interested in the idea of nanoparticle exchange, which has been done before by Weinstock and others. But we were interested for different catalysis reasons. Our idea was to take the polyoxometalate to stabilize the nanoparticles like this. And so that's our concept. And in the reality, it worked. You know, that's okay. That worked quite well. You can see that if we zoom in on one, this is TEM image, you can see one nanoparticle. There's clearly what looks like a monolayer of POMs surrounding it. And there was something else that got us thinking, actually. We always got these kind of darker blobs. And when we zoomed in on them, we can see that they were real supramolecular assemblies. This molecule, we characterized it by phosphorus NMR. Phosphorus NMR is just an excellent technique for this kind of hybrid because, like we saw earlier on as well, you've got the phosphates, which are completely embedded into the polyoxometalate core, and then you've got the phosphonates here. And they're all the characteristic signals, and we can monitor pretty carefully, pretty closely what's going on in any system. Again, like we've seen in all of the other systems, when we compare the redox potential of the P2W18, which is the dotted line, to that of the hybrid, the organic hybrid is far more positive in its first and second redox potentials compared to the P2W18. When we took this sample, this was soluble in various different things, but when we dissolved it in DMF, we put this POM on a TM grid. We just wanted to see what happened. And, well, you can see that almost nothing, really. There's, take my word for it, these black dots are POMs, and they're generally randomly dotted around the grid. But we'd seen these other things in our gold nanoparticle exchange system. And also, we've got massive difference, massive solvent effects on the colour. In DMF, our polyoxometalates are pretty bright yellow. In water, pretty strong brown. Now, quite a lot of work's been done on this in polyoxometalates before, looking at the supramolecular assemblies of it. So, you know, you can form micelles and vesicles and so on. So we were pretty sure that that was likely what was going on. And indeed, when we took our polyoxometalate, and it was an acid, so H6 POM, we added it into water, and we could see that after sharp heating, we formed fairly uniform micellar assemblies, which are probably vesicles, but some soft assemblies. You can see that they're relatively monodispersed. Now, I said before that this has been done before in parts. There's quite a lot of work on the supramolecular aggregation of polyoxometalates. But where we're interested, our perspective, is in the electrochemistry. And I showed you a minute ago the difference between the tungsten 18 and the thiol POM electrochemistries. This one here is the thiol POM in water. And we'll go back, we can compare with the DMF in a second. But this is the electrochemistry of the micellar assemblies. So here we have our reduction is now going this way. I do apologize. In Britain, reduction is always on the left, and in Japan it's always on the right. So data that comes from the different labs is always the other way around. So, as we reduce the polyoxometalate, as we reduce the micelle, we have this peak here, and then another reduction, and then a reoxidation, and again a reoxidation. Now, what we have happening here, though, is with this forward process, this one peak here corresponds to 1 electron and then 2 electrons. This is measured with a dip probe in situ electrochemical reduction. So it's a really, really nice way because you can get full spectra really quickly as you electrolyze a sample. We then scanned it back to here, to the oxidized side, and you can see that we go up 1 electron to 2 electrons, and then we go all the way back down from 2 electrons to 1 electron to no electrons. So we've got this kind of reversible micellar electrochemistry thing. What's more, this is very, very obvious when it's happening, because you can see one of them is dark blue and one of them is yellow, and this is totally reversible. Importantly, the DLS matches up before and after reduction and then after reoxidation, and it does for more cycles as well. Now, so this looks like we've got this, somewhat reversible electrochemistry in the POM micelles. A really interesting thing about this, though, is that as we look at the NMRs of the systems, if you look in DMF is where I showed you before, when I said phosphorus NMR is a brilliant tool. Look how good it is here. We've got 1 peak for the phosphonate groups and 2 peaks for the phosphates inside the POM. But if you look down here in water, in the same spectrum, those peaks are basically gone. As we add DMF to that, they grow back in. The same thing happens over here. Here in our proton NMR, we've got peaks which correspond to all of the groups we expect to see. In the H2O sample, we don't. We've almost got no proton peaks from our samples. When we first saw this, we thought something bad's happened. This before we'd really done the TEM. But as DMF is added, dropwise or stepwise, the peaks that correspond to the organic groups roll back in. So we've got this kind of reversible electrochemistry of the micelles, and we've got this clear, solvent dependence on the NMR. What about if we combine it? So what we saw is that the dotted line here is the micellar assembly electrochemistry. And as we added in DMF, we start to return to this molecular electrochemistry. We go back more positively. Now, if I can wind your minds back right to the start, I showed you the picture where I had one POM electrochemistry in acetonitrile or DMF and one in water, and the water one is far more positive. So here we've got the other way around. The water one is far more negative. And what this means is that these POM aggregates are having a major influence. The electronic structure is changing through the formation of the aggregates, and we think it's through Coulombic repulsion, i.e. when we have the micelles, it's more difficult to add electrons to them through repulsions. So we're having a look, and we'll try to get to the bottom of it soon. So yeah, just to summarize, that's the areas in which we work. Most of this work is being done in Japan, whereas this section here is more towards Nottingham. There's a lot of people I have to thank. Sumitra wasn't here at the start, so I have to thank you again for the invitation. I've got there's brilliant people who have contributed to this work, particularly Kati, who's an incredible postdoc who worked with me for a while, Jamie and Satomi in Japan. So I was assistant professor in Japan for 4 years, and I've been still looking after the group in Japan since I left. So a lot of people have done incredible work. Collaborators, David Robinson for calculations, and others. Finally, I just want to thank you. It's a wonderful opportunity to be here, and yeah, it's my pleasure to talk to you. Thank you.
Lecture. So we have time for a few questions.